Welcome everyone. Welcome to today's lecture. And in the last class, we started with the optics PYQs of IIT JAM Physics. So we discussed the wave optics PYQs of 2024. Basically, I explained the two questions in the last class, and if you haven't watched the video, you can watch it on in the previous video. And we have covered in the last class about the polarization concept and also the Newton's ring. In this class, I'm going to discuss a third problem which was there in 2024 IIT JAM exam, and this was also very important problem, and this was little bit difficult problem as such, and very few students were able to answer this question in the examination. So we will understand the concept first and then we will go for this problem. So the problem as such is from the topic of diffraction. So the topic is diffraction, and the subtopic that we have is a resolving power. So this is a question from a diffraction grating, how the diffraction gratings work. Okay, so before I come to the question, let's understand the diffraction gratings as such. So diffraction grating is a device which is used to resolve the light. Resolution for resolving this instrument is being used. So what happens is that you have a piece of some, either it is a metal or it is sometimes a transparent material. So you have a material and you draw very thin lines, very thin lines, 1, 2, 3, 4, thousands of line in very small area. So the lines are so small and they are so close to each other. Small means their thickness is very small. Small does not mean that the length of the lines is small. The thickness is small, and the lines are very close. They are so close that sometimes you can't even say that okay, there are many lines. It seems like it is a continuous thing. So many lines in a small space, and every line acts as a slit, just like a Young's double slit experiment, diffraction one slit experiment. Every sorry, sorry for that. Every light, or you can say every line, is acting like a slit. So it is a n slit interference or n slit diffraction. So let's say there are total n number of slits in your diffraction grating. So it is an n slit diffraction device. Okay? So we will understand what happens is that, and why it is used to resolve the lights. Resolution basically, or you can even say that, so let's say you have two wavelengths, you want to separate them, you want to see them, you want to separate a very closely spaced wavelengths. Diffraction grating is a good way to do that. Okay, so light gets actually split up, or you can even say that the fringes get split up. You get a many fringes on the screen, and or atomic spectrum, you see that when we study in the atomic spectrum, we see many lines, atomic spectral lines. So diffraction grating is used in that, so that on a screen the pattern is quite widespread. Otherwise, if you just observe the atomic spectrum, the entire spectrum is in this much region, and we cannot clearly analyze the two fringes or the two lines which are there in atomic spectrum. That is why we use a diffraction grating, so the diffraction grating can widespread the spectrum. It can spread the spectrum so that the spectrum is now on an entire screen, and now we can see, okay, where is every line is there. That is a purpose. There are two kind of diffraction gratings. One is a reflection and another is a transmitting. So in reflection grating, what happens is you have a metal or some reflecting material. The material will not transmit the light, it will reflect the light. So you have a material which is reflecting. So let's say this is a reflecting material. Okay. Now you put a opaque lines. Opaque lines means some sort of paint or color. Okay, so that the region does not remain reflective anymore. So let's say this line, this line, this line, this line. So these lines are the opaque lines. They will not reflect because their colors, paints, some sort of thing, coating is there. So now when the light will fall, light will reflect from this region, this region, this region, this region, this region, and every region is acting like a slit now. So we have a silvered surface, opaque lines, and the light is reflecting from the silvered surface. Since the light is reflecting, we call it as a reflection grating. So now this light, this light, this light, this light, and this light, all of them interfere with each other and gives you a pattern. and that is a pattern that we want to study in this class. When there are so many kind of lights are interfering with each other, what kind of pattern that we will see. On the other side, we have a transmission grating. In the transmission grating, what we have is a, again, the material is there, you can see, but now this material is transmitting material. For example, you can say is a very simple is the plastic. So plastic can transmit the light. So now again you put a opaque lines. So you put these lines. So now the light is not transmitting through these lines, these opaque lines, because these are paint or some sort of material. So light is not passing through these lines, but the light is passing through this 1, 2, 3, 4 transmitting areas. So when the light transmits from these 4 regions, all of 4 acting as a slit, and then when the light passes, all 4 rays interfere and gives you the pattern. In the first case, lights were reflecting from these regions. In the second case, lights are transmitting through these regions, and ultimately they all are interfering with each other and giving you the pattern. Okay. If you want to have this experiment successfully conducted, there are 2 things that you need to keep in mind, or at least one thing you need to keep in mind. That is the separation between the lines. Is this separation between the lines, or sometimes also known as the distance between the slits, should be comparable to the wavelength of the light. So the wavelength of the light is, let's say, 900 nanometer, then the separation between the lines should also be in the same order. Otherwise, you will not be able to see the diffraction pattern which is completely resolved, or you can say which is completely distinct. You cannot see all the fringes completely separated from each other. So that is one of the major condition to be conducting a diffraction grating or using a diffraction grating. Okay, let's say I have a light which is of the order of this wavelength, and also I am now trying to use this diffraction grating. So what kind of pattern I will see? So the pattern of a diffraction grating is something like this. First of all, I will teach you to learn to understand this pattern. So this is between I and beta. So beta in this case is an angle from the center of the screen. So let's say this is the center of the screen. As you keep on going away from the center, the angle keeps on increasing, the distance from the screen keeps on decreasing. So angle or distance, anything you can call it as. We will officially define beta, but for now you can understand beta is something which is basically a distance from the center of the screen or an angle from the center of the screen. Now you are measuring the intensity. Intensity of what? Intensity of a fringe. So this pattern suggests that at the center you will have a very bright fringe, very bright fringe. So let's say you have a pink color, or you are using a pink wavelength. So pink color will be very bright. Then you see the secondary maximas. They are the maximas, but very weak are there. So you will see again like this. They are still the fringes, but their brightness will not be that much. And then you have a secondary maxima. It is bright, but not as bright as the first one. Okay, not as bright as a primary maxima. So this is how your pattern is going to be, and in between the white region is your minima. So these are the minimas, because here you have no light is there. So in this pattern you see basically the 3 things. Number 1 is a primary maxima, which is a central maxima, very bright, one very bright light you will see. Then you have a secondary maximum lines, means then you will see the very dim sort of lines, dim lines. And then you see the secondary maxima. Sorry, again another primary maxima. So this is a, okay, sorry. So this is known as primary maxima. This is also known as primary maxima. And so this is primary maxima, this is also primary maxima, and in between you have the secondary maxima. Okay. One thing that you can see is that for the primary maxima, intensity keeps on reducing. So initially the primary maxima had very high intensity, then the primary maxima has less intensity, then the primary maxima has even less intensity. So the intensity of the primary maxima keeps on reducing. Okay. And between the two primary maximas you have many secondary maximas, or you can say very dim spectral lines or very dim colored lines. And then you also have third thing, which is minimas. Minimas is basically the absence of light. So this is a kind of a pattern that you see, and you have to focus on the three things: primary maxima, secondary maxima, and minimas. So first thing, primary maxima, very bright primary maxima, second bright primary maxima, third bright primary maxima, so on. Between two primary maximas, there are many secondary maximas, or you can say less bright lines, and between two secondary maximas, you see minimas, means white colored lines, which are where the light is not there. So this is a pattern that you see on the screen. Now, just a nomenclature, simple nomenclature you should know. We define few parameters. A is known as a slit width. D is the separation between the slits. Theta is an angle of the diffraction. Slit width means how thick is your slit. So when you are using the diffraction experiment, how thick is your slit? Means if I talk about the one slit, how thick is it? And then are what is the separation between these slits? Means, for example, they can be like this. This can also be the behave as a diffraction maximum. So this is your slit 1, this is your slit 2, slit 3. So you see every slit has some width. So let's say this width is A. And also the two slits are separated from each other, which is D. Okay? This can also be there. So this kind of thing can also be there. So A and D are the separation. A is the width and the D is the separation between the slits. Theta is an angle of diffraction. Okay, from the middle of the screen, where are you actually trying to look your maximas or minimas? You are trying to see the pattern at theta 10 degree, 1 degree, 2 degree, where you are trying to see your pattern. Okay. Okay. So diffraction, then you define two things, which is alpha and beta. I don't think you need this as much, but you can keep in mind. 2 alpha is defined as 2 pi by lambda a sine theta. 2 beta is defined as 2 pi by lambda d sine theta. So basically, what is happens in the n slit diffraction pattern is that both the things are happening. Interference is also happening and diffraction is also happening. So the combined effect is what you see in the screen. So this screen is a combination of the two patterns. One is interference pattern, and the second is the diffraction pattern. Combining them give rise you to the overall pattern that you are seeing. So that is what the idea is. Now we need some formulas before we can go to the question as such. So number one formula is, what is the intensity? So we draw the graph. We have drawn this graph, intensity as a function of beta. But what is the formula which is basically explaining this graph? So the intensity is defined as I equals to I naught sine square alpha by alpha square into sine square n beta by sine square beta. I naught sine square alpha by alpha square sine square n beta by sine square beta. So this is the equation which is following that graph. In physics, you should always know that whatever graph you have, what is an equation for that graph? Means this graph is based on which equation? How I made this graph? So this graph is made by I equals to I naught sine square alpha by alpha square sine square n beta by sine square beta. Clear? So this is your graph. Okay, cool. Or this is your equation. Very important. This you have to keep in mind. So this is you have to remember. Perfect. Now from this, we will talk about the three things: primary maxima, secondary maxima, and minima. So for primary maximas, we will maximize this thing. So we maximize this thing, and this thing will be maximum when beta is equals to plus minus n pi. So when beta is pi, 2 pi, 3 pi, 0, 4 pi, 5 pi, minus 2 pi, in that case, this thing goes to maximum, and that you can check using the L'Hopital rule. Because when you get 0 by 0 form, in that case, you can easily see that you might have L'Hopital rule, you get a maxima. So you know sine x by x. If you put 0, it is actually 0 by 0. But when you use L'Hopital rule, you differentiate above numerator and denominator. And now if you put 0, you will get 1. So the value of limit is actually not 1. It is not 0 by 0. Okay? So using the L'Hopital rule itself, I can say that this thing is getting maximum. This thing becomes maximum at what values? When beta is equals to n pi. So if someone asks you, where do you get primary maximus? So you get a primary maximus at beta equals to plus minus n pi. Okay. In a simple word, you can write it as d sine theta equals to n pi or n lambda. D sine theta equals to n lambda. Remember this equation where d is the separation between the slits. Separation between the slits. Okay. Sometimes this is also known as a period. We also call it as a period. Period is also known as a separation between the slits. Okay. And that was a major confusion in this question. I will come to that. So if beta is equals to plus minus n pi, what we learn from here is the d sine theta equals to n lambda. N is 1, 2, 3, 4, 5 or plus minus 1, plus minus 2, plus minus 3 or 0 as well. This thing becomes maximum. How much is this value? This value will be n ka square. You can use this L'Hopital rule and you can prove it. That will be your homework. So you put this, you find this limit. Okay, limit beta going to 0, sine square n beta by sine square beta will actually give you n square, and you can check that. You can check that, and this will going to give you n square. That is why the intensity will be n square I naught sine square alpha by alpha square. So that is the intensity of your maximas. Which maximas? Primary maxima. N square I naught sine square alpha by alpha square. Okay. So these are your primary maxima. Perfectly fine. Makes sense. And when do we get primary maximus? Beta equals to plus minus n pi or d sine theta equals to n lambda, where d is the separation between the slits. If you want to know secondary maxima, then what you have to do is you have to do di by d beta equals to 0. So you differentiate this intensity with beta and make it equals to 0. I haven't shown the mathematics because it's not very important for us. But if you want to do, you can differentiate this and make it equals to 0. You will get the values of betas where you are getting the secondary maximum. So for secondary maximum, we don't have to say so much. That's it. And then we come to the minimum. So first thing you always remember should be that there are n minus 1 minimas between two primary maximas. So between one primary maxima and between second primary maxima, there will be n minus 1 minimas. So n minus 1 minimas and n minus 2 secondary maxima. This column also you can keep in mind. Okay, there are n minus 1 minimas and n minus 2 secondary maxima. Okay, in our case, it is n minus 1 minimas. Okay. N is a number of slits. How many slits you have? Clear. So this is one point. And now minimum means intensity is 0. So we are trying to make intensity 0. We're trying to make intensity 0. So sine square n beta should be 0, or you can say sine n beta should be 0, but sine beta should not be 0. Otherwise, the denominator will go to 0 and the problem will happen. So sine n beta is 0, but sine beta is not 0. So sine n beta 0 means n beta equals to m pi. M is 1, 2, 3, 4. So if n beta is m pi, then you can put your value of beta. So basically, you will get d sine theta equals to m lambda by n. So this is also important. D sine theta equals to m lambda by n. So this is going to be your conditions for the minima. So where are you going to get the minima? So this was your entire idea of the diffraction grating. Diffraction grating is n lines, n slits. The graph is primary maxima, secondary maxima, again primary maxima, secondary maxima, again primary maxima. So we saw the equation for primary maxima, we saw the overall intensity equation, we saw the secondary, how to get secondary maximas, and what is the condition for the minima. So these are all the very important things, and you should have that in your formula sheet. Okay, what are the things I need to keep in mind for diffraction grating? Now comes the next point, which is resolving power. What I have to do for the resolving power? So resolving power is an ability to separate two closely spaced fringes. So now I am bringing you from a topic of diffraction to the resolving power. Because the purpose of this graph or this diffraction grating was to resolve the light. So now we have to understand that. So resolving power means how much you can separate the two very closely spaced fringes or two very closely spaced objects. That is all resolving power is. Resolving power has basically two formulas. One is the general formula, which is applicable for resolving power of everything: telescope, microscope, any apparatus. This is the formula for reflection rate. That is lambda by delta lambda. So let me explain that. For example, if some instrument is there which can resolve 4290 and 4892 angstrom light. So let's say there is some instrument which can separate these two wavelengths. So first of all, we find the average. So average is 4891 and the delta lambda between them is 2 angstrom. So this is going to be the resolving power. So the resolving power is going to be almost, you can say, 2445.2. So this is the resolving power of your instrument. Basically, if you want to resolve these two wavelengths, this much resolving power you need. Okay? So that is the idea. If the resolving power is more, you can even resolve more closely spaced. Means your instrument will be able to differentiate between this wavelength and this wavelength. It will separate them out. Means you will see one wavelength here and one wavelength here. So that is how we define the resolving power, lambda by delta lambda. In the diffraction grating, there is another formula which is known as Mn. M is the order of resolution. Means first M is 1, 2, 3. Which maxima you are talking about? First primary maxima, second primary maxima, third primary. What is a maximum or M? Basically, you want to know the first order resolution. Basically, you are within the first primary maxima or you are within the second primary maxima. M is that. And N is the number of lines. So the resolving power for diffraction grating is defined as M into N. So now this was all the data you needed for this problem. And now we will come across the question. What is the problem that we need? So the problem is something like this. When a system of multiple long narrow slits. So this was a question which was asked. So there is a system of multiple long narrow slits. Width of the each slit is 2 micrometer and the period is 4 micrometer. Okay? Period is basically D, or D is defined as A plus B. Okay? A plus B period. We define D. D is the period, or you can say the separation between the slits, which is 4 micrometer. So this is directly given to us. What is the separation between the two fringes? So that is going to be 4 micrometer. Is illuminated with a laser wavelength of 600 nanometer. So the wavelength is given, which is 600 nanometer. There are 40 minimas between the two consecutive principal maximas. So you know how many minimas are there between the two consecutive primary maximas? N minus 1. So n minus 1 is 40. It means n is 41. Then they are asking what is the maximum resolving power of the system. So the resolving power of the system is decided by R equals to M into N. I already know N, but I don't know M. I don't know how many primary maximas will be there because I need to know maximum resolving power. For maximum, my M should also be maximum. So I don't know how many maximas will be there. How many primary maximas are there? 1, 2, 3, 4, 5, 6. How many? So for that, we can use the formula d sine theta equals to m lambda. So this is nothing but d sine theta equals to m lambda. And you know for maximum, sine theta will be 1 because only thing that you're changing is angle from the center or the distance from the center. So sine theta is going to be 1. So you can say that m is given by a plus b by lambda, or you can say d by lambda. D is given to you, it is 4 micrometer. So 4 micrometer divided by lambda is 600 nanometer. So 6 into 10 to the power minus 7. So this is 20 by 3. So 6.67. So there is nothing as 6.67. Either you will have 6 maximums or you will have 7 primary maximums. You cannot have 7 because you cannot go beyond 6.67. So the number of primary maximums that you will see is 6. So only 6 primary maximums you can see. So M is going to be 6. Now number of slits we already found is 41. Now we can do the resolution. Resolution is going to be M into N, which is 6 into 41, which is 246. So total number or total resolution of this system is 246. I have checked that some institutions have solved this problem wrong. So answer, actually I checked with the IIT JAM exact paper, it is going to be 246. So 246 is the correct answer. So that was your entire topic of diffraction grating. So so keep watching the videos. In the next video, I'm going to do the you can say thin films, and I'm going to solve IIT JAM 2023 problems. So I will see you all in the next video now. That's all for this today's class. I will see you all in the next class.